And good evening and welcome to the Kennedy Space Center, where you are looking live at a nearly fully fueled Atlas V rocket on Space Launch Complex 41 at the Cape Canaveral Air Force Station. I am Chris Gebhardt, Assistant Managing Editor at NASASpaceflight, and if you are bored by the Oscars, we promise a much more exciting show here from the European Space Agency, United Launch Alliance, and NASA tonight. We are here waiting for the launch of the Solar Orbiter mission from the European Space Agency in cooperation and collaboration with NASA. This is an exciting mission to study the sun, and it's actually kind of a companion mission to a NASA solar mission that launched a year and a half ago on another United Launch Alliance rocket, the Delta IV Heavy, and that mission, of course, is the Parker Solar Probe. And both missions are kind of wanting to answer very similar questions about the sun, but both are going about getting those answers in very different ways that will actually allow us to have, for the first time ever, a complete full view of our parent star. And that is really, really super exciting. So we will be with you throughout the launch window today. Hopefully they go right at the top of the window. Right now, the United Launch Alliance says that everything is on track and they are working no technical issues that would delay an on-time liftoff of the Atlas V at 23:03 EST, which is 04:03 UTC and 5:03 Central European Standard Time. For those of you joining us from Europe, and welcome from around the world to from wherever you are watching. Let us know in chat here on this stream where you're watching from. And likewise, if you have any questions about Solar Orbiter, about the Parker Solar Probe, the companion mission to this one, about the Atlas V rocket, about United Launch Alliance, or heliophysics in general, let us know. Throw those questions up in chat. A big shout out to Michael Baylor, who is once again directing our stream from behind the scenes. He is the man making all of this work. He's going to be passing and relaying those questions to me, so throw them up in chat. Along with Jared, who is also a member of the NASA spaceflight team, who will also be relaying questions to me and is helping behind the scenes as well. So, a big mission. We are launching to the sun. This is a flagship medium-class mission for the European Space Agency, the first medium-class mission that is part of their a sort of decadal survey that the European Space Agency wanted to do to answer some very fundamental questions about the physics of the universe, and specifically how the sun generates the heliosphere and the solar wind that dominates a large part of our solar system out to 120 astronomical units from the sun. One astronomical unit is 149.6 kilometers, 149.6 million kilometers. And the heliosphere extends out to about 120 of those astronomical units. And how do we know how far out the heliosphere extends? That's all thanks to two little intrepid NASA probes that were launched in 1978 called Voyager 1 and Voyager 2. Those probes are remarkably still functioning. I mean, they're both well over 130, 128 astronomical units away from the sun at this point. But Voyager 1 crossed out of the heliosphere and entered interstellar space at a distance of 121 astronomical units back in August of 2012. And Voyager 2 followed on a different trajectory toward the southern part of the solar system, if you consider the sun's equator, and then go up from that is north, goes down from that is south. And Voyager 2 exited to the Voyager 1 exited to the south. Voyager 2 kind of kept on the equatorial plane there of the sun and exited at a distance of 119 astronomical units on the 5th of November 2018. So they have returned immense amounts of data from the entirety of the heliosphere, from Earth orbit at 1 astronomical unit all the way out to when they exited it. And it was a continuous stream of data that they returned to us that was absolutely invaluable, and that no one could have imagined them providing when they were launched by Titan rockets in 1978 right here from the Cape Canaveral Air Force Station. So the Voyagers are way out. They've passed out of the heliosphere, so they actually can't give us any more data on it because they're outside of it now in the interstellar medium. But while they went outward, the solar orbiter is going inward. And that brings us to the first question that I'm sure absolutely everyone has. We are launching to the sun. Why are we doing it at night? Well, the joke answer to that is because we have to launch to the sun at night so that the sun doesn't see us coming. That's the nice joke that we told ourselves at 3:30 in the morning when Parker Solar Probe was launching, and it's the joke we're going to tell ourselves again for this 2-hour-long launch window that opens at 23:03 Eastern and closes at 1:03 Eastern, or 4:03 UTC to 6:03 UTC. Today. Now, the actual answer to why we are launching tonight when we are launching to the sun is because we are not actually launching to the sun. We are launching to Venus. And the every 8-month Venus interplanetary window opened on the 5th of February. It closes on the 20th of February. That is the duration of our launch window. Of course, we will have a successful launch tonight, and we won't have to talk about this, but if for some reason Solar Orbiter were to miss this current window that closes on the 20th of February, we would have to wait until October again for the next opportunity to launch this mission. And the reason we're going to Venus is because it's actually by going to Venus that we can get close to the sun. So our rockets have a bit of a problem when it comes to launching things toward the sun. It's very, very difficult to launch to the sun because you have to accelerate so fast to get out of Earth orbit. But to get to the sun, you have to slow down. And you can't do that with a rocket here on Earth because what rockets are trying to do is get you away from Earth, to get you on your way to where you're trying to go. This is not a problem when we're going to Venus, when we're going to Mars, or any of the destinations outward from Earth, but it becomes a problem when we're trying to get really, really close to the sun because a rocket can't accelerate you and decelerate you at the same time. So we use Venus to slow down. We use multiple gravity assist flybys of Venus and Earth for this mission to slow the probe down after Atlas V has successfully launched it. And by slowing it down, that brings the probe's solar-centric orbit or heliocentric orbit down to just 0.28 astronomical units, actually inside the orbit of Mercury, while swinging it out to 1.2 astronomical units, which is a little bit farther out than Earth orbits the sun from. So we have to launch to Venus because Venus is what allows us to slow down. Now, for this mission in particular, in order to view, the sun is massive, right? So in order to view the solar poles, we have to change the orbital inclination of a probe. But we can't do that with the rocket as well, right? The rocket has to launch it on the ecliptic plane of the solar system so that it can intercept Venus. So we are using Venus to not only slow the probe down to get it closer to the sun, but also to change its orbital inclination to 28 degrees relative to the sun's equator during the 5-year primary mission that will begin after a 2.5-year process of getting it into its initial science orbit. And then if the mission is extended beyond 7 operational years, 5 science years, if it's extended out to 10 years, that orbital inclination will shift even higher to 33 degrees. And that's all using flybys and gravity assists of Venus. So that's why we're launching at night, because this time of year where Venus is in relation to Earth, to get to Venus, you have to launch at night, and you have to launch in this 2-hour window today. Now let's also talk, and I see you've got some amazing questions already, and I will be getting to them very quickly. So if you have questions, keep throwing them up into chat. Jared's doing a great job of getting them to me. But the other reason we need to talk about our launch window tonight is that even though it's 2 hours long, we cannot launch every single minute of that window. And that's because in order to get to Venus throughout this 120-minute window, there are 120 different trajectories, one trajectory for every minute, that the Atlas V would have to be programmed to fly. And that's a lot of different trajectories, right? So in order to simplify things, what United Launch Alliance has done is created 25 single-second instantaneous windows, one every 5 minutes, in which the Atlas V can launch. So if we can't go right at the opening of the window at 23:03 Eastern, the next option would be 23:08 Eastern, followed by 23:13, followed by 23:18, followed by 23:22, and so on and so forth until the end of the window at 01:03. So that's another reason that these interplanetary missions, especially to Venus, are very complicated because of the trajectory that the Atlas has to fly. Now, a big shout out to Declan Murphy earlier today, who got the answer of this for me, because the speed at which the Atlas V has to accelerate solar orbiter so it's on an Earth escape heliocentric transfer orbit to Venus is 12.03 kilometers per second. That is faster, much, much faster than the International Space Station, which goes about 7.8 kilometers per second. So that is the type of speed that Atlas V has to accelerate the probe to. Now, Solar Orbiter is relatively small compared to other probes. It's very light compared to other probes. That comes in only about 1,700 kilograms. But in order to accelerate that much mass, and you also have to accelerate the Centaur upper stage to that velocity as well. So in order to do that, that's why we have one strap-on solid rocket motor on the Atlas, because the Atlas alone can't do it. So it needs that extra 90 seconds of performance from the single solid rocket in the opening minute and a half of flight in order to have enough propellant reserves in the Centaur to complete that acceleration. Because at the end of the day, orbit is all about acceleration, and you have to be going 12.03 kilometers per second for this particular mission to nail that transfer orbit to Venus. So buckle up, folks. As I said, sorry guys, give me 1 second. Thomas is showing me something. Oh, interesting. Okay. Sorry guys, my colleague Thomas was showing me something that Michael was trying to tell me from behind the scenes here. So my apologies for that. Bear with me here. Okay, so that's so anyway, let's start taking some of your questions. Again, if you've got questions, throw them up in chat here and we will get them answered as we head toward the opening of our launch window in about an hour and 5 minutes from now. So we are getting close. At this point in the countdown, Atlas V is nearly completely fueled. They should be almost completing fueling process or completing the fueling process at this time. So let's start taking some of your questions. So Kenji Okura wants to know what happens to the second stage after it separates from solar orbiter. An excellent question. So it is also on a Venus intercept heliocentric trajectory at spacecraft separation. But in order to change its orbit so that it doesn't intercept Venus at the same exact location that solar orbiter will, United Launch Alliance actually does what's called a blowdown, where they sort of open all the propellant valves, vent all the tanks, their pressurization, and that action alone changes the velocity of Centaur just enough so that it doesn't intercept Venus to do the same thing that solar orbiter is doing. But this Centaur upper stage will be forever on a heliocentric orbit that goes about as close to the sun as Venus and comes back out to Earth level, and it'll just keep doing that forever until it either hits something or or hits a planet, you know, and burns up. But that's a great question. That it is on the same trajectory and the same Earth escape trajectory as solar orbiter will be. So Kevin Swalls wants to know, how do they get spacecraft near the sun? Anything closer than 10 million miles from the sun would burn up. Yeah, so how does the spacecraft survive? So we went over the physics of how they actually get the probes there in their orbit. But in order for them to survive, just like the Parker Solar Probe that has a heat shield protecting all of the instruments, Solar Orbiter also has a heat shield as well. And that heat shield will always be facing the sun to protect all of the instruments on board this craft. But a really, really cool thing about this mission is that because of what it has to do, because of the cameras and the instruments that are doing the active science every perihelion, every time the probe passes closest to the sun, there are cameras and instruments that have to look directly at the sun, but they can't do that because the heat shield is there. So ESA engineers, and this is truly ingenious, have designed a heat shield that has doors. So every orbit that this probe does, only 10 days are active science gathering days. The rest are sort of passive remote sensing days. So it's always gathering data, but the active part of the investigation is only 10 days long each orbit. And during those 10 days, the doors on the heat shield will open, exposing the instruments to the heat, the light, the intensity of the sun. So in order to compensate for that, ESA engineers had to design these instruments to discharge that heat backward and safely away from them through the radiated cooling systems that are on board Solar Orbiter. It is an immensely complex mission that really, just like Parker Solar Probe, we didn't have the technology to do until today. This is a mission that heliophysicists have been wanting to do for a very long time, but we just didn't have the technology to do it until now with that heat shield. So an absolutely great question about how this probe is going to survive getting that close to the sun there. Astro FPV wants to know how many gravity assists will they be undertaking in order to achieve its final desired orbit. A great question. So it'll take about 2.5 years to get Solar Orbiter into its primary science orbit. And it'll intercept Venus once every 8 months or so, is the plan. So it would take about 5 or 6 gravity assist flybys of both Earth and Venus in order to get it into its primary science mission. But after it's in that primary science orbit, it will keep encountering Venus periodically to continue to change that orbital inclination ever higher, so it can see, so it can get those views of the of our sun's poles, which we have never seen before. So we don't actually know how the sun's poles affect the creation of the heliosphere, affect the creation of the solar wind, or even what role they have in the creation of coronal mass ejections, which could really wreak havoc on not just our space technology, but our equipment and communication systems here on the ground. That is the NASA security helicopter going by, patrolling the Kennedy Space Center and Cape Canaveral Air Force Station land to make sure everything is safe and secure for the launch of Solar Orbiter today. A great question, guys. Keep your questions coming. These are really, really awesome. Stephen Kaser, I hope I said your name right. Apologies if I didn't, wants to know how close would the solar probe be to the sun? So it will get as close as 0.28 astronomical units. So an astronomical unit is 149.6 million kilometers. So 0.28 of that is how close Solar Orbiter will get. It will get within the orbit of Mercury. But it is much, much farther away than the Parker Solar Probe, which actually dives into the solar corona to do part of its scientific mission. So this is one of the really cool things about these two probes and why they're companion missions, is because Parker Solar Probe seeks to answer these very similar questions by literally diving into the sun, while the Solar Orbiter takes a step back and looks at the sun and the corona from above it. Which is really cool about, which is really, really cool for how these two missions work together. Sam Adams, I am not in Cocoa Beach. I am at the Kennedy Space Center press site about 3 miles away from the launch pad. Looking at it here. Hopefully, if you're in Cocoa Beach, you're going to get a heck of a view of this thing as it launches. The skies are mostly clear, just patchy clouds, but at least right now, absolutely nothing to worry about. We did hear an update to weather. Weather is 90% favorable for the duration of our launch window tonight. That is up from an 80% chance of acceptable weather earlier today. So weather definitely trending in the right direction for us here today. And again, if you're just joining the stream, if you've been tired of the Oscars, we promised you a much better show today, and ULA and ESA should definitely deliver that for us here. But if you're just joining us, we are here covering the launch of the Solar Orbiter for the European Space Agency in collaboration with NASA, launching on an Atlas V 411 rocket, a 4-meter payload fairing, a single strap-on solid rocket booster, and a dual-engine Centaur. And a single-engine Centaur upper stage. So keep your questions coming, guys. So Jess wanted to know how long this mission will last. It'll take 2.5 years, 2 to 2.5 years to get into its primary science orbit, then 5 years of a primary science mission, so a total of about 7 years, with the ability to extend that to 10 years if the probe is still functioning perfectly after those initial 7 years. So Raul wants to know what fuel is used. Excellent question. So the solid rocket booster uses HTBP and aluminum to burn solid propellant for this mission. The Atlas booster itself uses RP-1 rocket grade kerosene and liquid oxygen, and the Centaur upper stage uses liquid oxygen and liquid hydrogen. So Zachary Sellinger wants to know, why will the Atlas V use the RL-10A on the Centaur instead of the frequently used RL-10C engine in recent days? It's a good question. I didn't actually know that they still used the RL-10A on.
So the dual engine.
So Thomas can answer. So Thomas can answer this. Yes.
Yeah. So the dual engine Centaur, which you would have seen on the Starliner orbital flight test mission, and you will see much more frequently going forward as they're looking to transition all Centaurs to dual engines, will use the RL-10A4 variant of the RL-10 engine. However, single-engine Centaurs are still using, to my knowledge, the RL-10C.
That's what I thought
engine.
too. Yeah.
So, and this configuration, the 411, is a single-engine Centaur. So this will be using the RL-10C engine, if I'm not mistaken.
That's what I thought too. Yeah, that the single engines don't use the A. Yeah. But we'll check on that, Zachary, just to make sure. But nothing in the literature. Okay, so it is using the RL-10-4A for this mission. Michael just told me that through the chat. So it is an RL-10-4A. It's a great question why they switched. We'll ask. I don't know that off the top of my head, so we'll find a ULA representative here after the stream is done and go ahead and ask that question. You know, the RL-10-4A, the RL-10C, they have different thrust parameters, different specific impulses that they use. So it's likely just that this mission required a different specific impulse from the Centaur engine, a different maximum thrust from the Centaur engine, and that's why they did it. But we will find out for you the actual answer to that. Thanks for pointing that out. The Kerbal King wants to know, is there a reason why the solid rocket booster is held onto for so long after it burns out? And the answer is yes, there is a reason for this. So because of the trajectory that the Atlas V climbs very steeply in its initial first stage flight, and because of that very steep climb, by the time it's 1 minute 30 seconds into flight when the booster burns out, it's still too close to land to separate, because if upper level winds were just right, it could blow the booster back to land. So they hold on to that booster until like 2 minutes 12 seconds, something like that, and then jettison it at that point when the Atlas is far enough downrange from the Cape Canaveral Air Force Station that popping that booster off at that time does not pose a threat to land. And a great question, because yeah, it is weird that normally when you burn out a stage, you jettison it instantly to get rid of that weight, but they actually sacrifice just a little bit of performance to carry that booster a little bit further. And the same is true for the 2 solid rocket configuration of the Atlas. They hold on to those boosters a little bit longer. It's when you get to the 3, 4, and 5s that they pop off almost right when they burn out, because it's far enough downrange at that point. But another reason too is that you need to be high enough in the atmosphere so that your airflow doesn't permit recontact of the solid as you pop it off. And 90 minutes into flight is just as only 30 seconds past max Q, moment of maximum aerodynamic pressure. So it's a combination of the threat to land and the aerodynamics that are still streaming across the Atlas at SRB burnout as to why they hold on to that for so long. Kerbal Essence wants to know, why was the Atlas V chosen over the Falcon 9? Well, this comes down... Thomas, do you want to take this away? Because this comes down to the C3 value, and you're better at explaining this than I am.
Sure. So basically, there are so many variables that come into these trajectories, especially when you get into interplanetary missions with multiple flybys of Venus, for example. So there's a lot of different factors that come into that. One of those is simply how much energy you can put into the payload that you're launching. And one very big perk of using liquid hydrogen as a fuel, as the Centaur upper stage does, is it is very efficient at converting its fuel into kinetic energy. Therefore, the Atlas V has a big advantage over some other rockets, such as Falcon 9, which uses RP-1 in its upper stage, on these interplanetary trajectories. Now, every mission is different. Every mission has different requirements, so there's a lot of factors that go into that. But that is definitely one big leg up that Atlas V has. And of course, you know, just overall, Atlas V is a near perfect launch vehicle. United Launch Alliance is a very reliable rocket, and when you have a mission as high profile as this, that's definitely another thing they're going to take into consideration.
And the Falcon 9 is a very reliable launch vehicle as well, but you know, the launch vehicles are chosen many, many years before launch.
Absolutely.
Right? So it's a little unfair to compare SpaceX's wonderful success record and flight and rapid flight schedule that they have now, because you really have to go back to 2014 when the launch vehicle was selected for this mission, you know, to consider all of those variables that NASA's Launch Services Provider program had when they were deciding and soliciting and examining the bids for this particular mission, because this mission was actually supposed to launch in 2017, and then it got bumped to 2018, and then it got bumped to 2019, and now here we are in 2020. So the launch vehicle was chosen 2014, a long time ago. So it's a little unfair to compare the two agencies to where they are, the two companies where they are now versus where they were in 2014. But I hope that answered your question.
Yeah. And also, just as a sense of, you know, keep in mind the context here, it might seem like it wasn't, you know, that long ago. 2014 was before a single Falcon 9 ever landed. So we're talking very drastic different scenes.
And also before Falcon 9 full thrust
That's
was
true.
a thing, before the Block 4s, before the Block 5.
Different.
The performance of the Falcon 9 was not as high as it is now. So while a Falcon 9 could do it now, you know, Atlas V had the edge back then when the mission when they had to decide what launch vehicle would use, and which is why I say it's a little unfair in this particular case to compare why one was selected over the other. But I hope that gives you the answer. So DOS is asking me through our internal comm system that asking if SpaceX has done any interplanetary missions to date. This is a yes and a no answer. They have, in the sense that the very first test flight of the Falcon Heavy sent the Tesla Roadster into a trans-Mars injection burn. It threw its orbit out farther than Mars into the inner asteroid belt, and so they have demonstrated that they can throw a payload that far, but they have not actually done an interplanetary mission yet. They have launched the TESS spacecraft, which, you know, used the moon to sort of fling out into this really weird orbit of Earth. They've done some really cool things, but they have not actually launched a probe
The closest thing I can think of is the Discover probe, which
Right.
which of course, not really interplanetary, but it did go to the L2 Lagrange point,
Yes.
which is, much farther than, any of the geostationary satellites they would have launched. So that's like that or TESS are the closest things they've done so far.
And
But
then
they've
that
got,
car out to Mars distance orbit.
and then the sports car.
Yeah.
But the I think upcoming another thing that's kind of close, they have the asteroid or the asteroid deflection dart,
mission.
right? Yeah.
Yes.
So that's another one that'll be Earth
And
escape.
that'll be the first true, like, what we would think of as interplanetary Earth escape, going and rendezvousing with another body away from Earth. That's next year, is it not? 2021
I could check on
or
that.
2022, something like that. So yeah, so Elizabeth A also wants to know, will the added solid fuel affect the look or sound of the launch? Yes and yes. So the RD-180 engine burns very orange, and the single solid rocket will burn very white. So it will be a much whiter look to the overall launch plume in the initial 90 seconds of flight. The solids always produce way more sound than liquid-fueled rockets or engines, so there will be a tremendous crackling sound here too, as well. But the single solid rocket will also provide a wonderfully weird look to this rocket, where it's power sliding to the south. So if you're looking on this screen, when the single booster ignites, the Atlas will actually translate to the right of your screen as it comes off the pad, and it'll have a huge asymmetrical plume to it. So definitely the single solid affects the look and the sound and the feel of the launch. So let's keep going, because this is really and keep throwing me your questions. Jared is continuing to send them to me here behind the scenes. So does the single solid rocket cause any issue with orientation, and if yes, how does the Atlas V correct it? Excellent question, because oh yes, it does. The simple answer is that it creates so much asymmetrical thrust that the RD-180 main engine on the Atlas has to be gimbaled to counteract that, so that the Atlas can still fly a straight and true profile like a normal rocket does. Here's the much more complicated answer to that. Rockets fly by firing their engines through the center, so to align the center of thrust through the center of mass of the vehicle. And the center of mass is constantly changing as propellant is depleted, as the stages separate, and all of that. The single solid rocket nozzle is canted in a fixed position of 3 degrees, which helps realign the center of thrust closer to the center of mass. But the RD-180 still has to gimbal through its thrust vector control system to finish that realignment of the center of thrust through the center of mass of the rocket. Now, this is actually sacrificed in the first few seconds of liftoff, when the engines are all locked in place as it comes off the pad, which is why it sort of will power slide to the right of the screen here initially, before the gimbaling really takes hold, and they do that. But the RD-180 has to be, the gimbaling of the RD-180 is constantly changing through SRB flight, because as propellant is depleted in the SRB and in the Atlas booster itself, the center of mass is changing, so you have to continuously readjust that center of thrust, or where that center of thrust is, with the gimbaling of the RD-180, and that's how they do it. That was such a we went back and forth in our launch article about how we were going to describe this, so I'm really glad you asked that question, so we could get the really technical answer out on the stream, because we erred on the side of readability in the launch article for it. But yes, that's how it does it. That's how it compensates, and it is specifically because of the gimbal range and the thrust vector control systems on the Atlas that it can fly with a single solid rocket. Atlas's successor, the Vulcan rocket, will use Blue Origin-made BE-4 engines, which do not have the same gimbal range as the RD-180, and that is why the Vulcan successor will not be able to fly with a single or asymmetrical solid rockets. It will have to fly with either none, 2, 4, or 6, whereas the Atlas V can fly with 1, 2, 3, 4, or 5 boosters, and the gimbaling corrects for all of them. But it's definitely more of a challenge for the Atlas with a single solid than it is with 3 or than it is with 5. just because of that huge asymmetrical thrust.
And it's worth noting that even the 3 and 5 booster configurations of Atlas the boosters aren't actually mounted symmetrically for those configurations.
They're not.
They're slightly asymmetrical just because of how the plumbing on the outside of the booster lays out. You can't actually place them symmetrically. So on those types of missions, the RD-180 is doing the same thing. It's to a less drastic extent and it's less visible, but it is actually doing that same thing of counteracting the asymmetrical thrust from the boosters. Only the 2 and 4 boosters segments are actually symmetric.
Right, but the Atlas is not the only rocket that has used asymmetrical thrust. The most famous one, I would argue, is the Space Shuttle, which had huge asymmetrical thrust with the twin solid rocket boosters and then 3 massive liquid-fueled main engines, not only offset from the center of mass and the center of thrust from the vehicle, but then those engines were even under normal configuration or zero gimbaling, were even canted even more, right? It was an amazing vehicle to watch launch in that regard. So please keep your questions coming. I've got a whole list of them. I have not forgotten any of you. We are going through them in the order that you guys asked them. So keep sending them and we'll keep answering them. So Drone Flights AZ4K wants to know, do the trajectories all taken, so the 25 discrete trajectories tonight for the 25 single-second launch windows every 5 minutes for 2 hours tonight, do those trajectories all take into account any type of collision avoidance or anything else in orbit or in its path? They do not take into account collision avoidance with other satellites or any debris that's up in orbit. But what happens is United Launch Alliance's team is communicating with the Air Force Space Command in Colorado, which tracks all of the everything that's in orbit of Earth, and they confirm with the Air Force Space, or Space Force Space Command now, I guess it's technically called, to confirm that each trajectory will not intercept something in orbit. So what you'll hear over the nets is that they will verify that there are no COLAs, which is an COLA, which is an acronym that stands for collision avoidance. And if there is a COLA, they will, for a particular trajectory, they will just simply not launch in that moment. So let's say this is entirely hypothetical. Let's say hypothetically they can't launch at 23:03, so their next opportunity is at 23:08 Eastern, but the trajectory at 23:08 Eastern would have a collision probability with something in orbit, so there would be a COLA cutout. They would simply not launch at 23:08 and go to the next one, which is at 23:13. That's how they would do it today. And that's true for every single launch. It's not just this one today. Every single rocket launch in the world will look to see if it has any possibility of colliding with something. There was a Rocket Lab Electron launch last year. There's a couple that have had collision avoidance cutouts within the window where they haven't been able to launch for 2 or 3 minutes of time to make sure there was enough separation distance. So it does happen. But the trajectories themselves do not take that into account. But that's a great question. That's a great question.
They are with the International Space Station, which has, of course,
yes,
very strict guidelines as to how close we can launch rockets.
There was one a couple years ago that had a collision avoidance with the International Space Station.
I think it was one of the Rocket Lab ones.
Yeah, so it even happens with the stations. Sometimes the station's the thing we might collide with, and we really don't want that to happen. Spacelock Engineering wants to know, how does the rocket get out of Earth's gravitational pull? And your question is that applicable to like the moon? And the question is yes. It is the same way that the Atlas will do it today is applicable to how any rocket would do it, no matter what celestial body you're trying to get away from. It all comes down to velocity. You have to accelerate the Centaur upper stage of the Atlas and its payload to Earth escape velocity. In the case of this mission tonight, that escape velocity is 12.03 kilometers per second, which is the needed escape velocity to get away from Earth and send the probe on the correct path to Venus. And that's how you do it. You calculate what the escape velocity is for a given body based on its gravitational pull, its gravitational well in the fabric of space-time. And that's what you have to accelerate beyond in order to escape Earth. And that goes not just for Earth, right? Like the Voyager probes were accelerated not just to Earth escape velocity, but solar system escape velocity, which is much higher than the speed we're talking about today. But it all comes down to velocity, and that's how you escape from the gravitational pull of a body. It varies from body to body. To get out of the gravitational pull of the moon takes far less speed and energy than it does to get away from Earth. Getting away from Jupiter would take a significant amount of more energy and speed than it takes to get away from Earth. So it all just comes down to the size of your body and the gravitational pull. Tom Cross, Tom, hey, how are you doing, man? Great to see you on here. So Tom has a great question here too. When the solar probe is in its polar orbit of the sun, how does it count a year? Does it still count a year in terms of in terms of how long it takes to just complete one orbit? And how many years will the probe experience compared to us here on Earth? Great question. So when we say that it takes 2.5 years to reach its science orbit, a total mission of 7 or 10 years, we measure that by Earth years. The probe will experience more. The probe will take about 8 months to orbit the sun, about the same amount of time it takes Venus to orbit the sun. A little bit different because it doesn't encounter Venus every single orbit that it does, but it takes roughly 8 months for this probe to complete one orbit of the sun. So the probe will be experiencing a year every 8 months, but we count the years that the probe is active in terms of number of Earth years. And we do the same for our rovers and our fleet of vehicles at Mars and at Jupiter, and for the Voyagers as well, way out there beyond the heliosphere, where we still count Curiosity as having been on Mars for 7.5 years, but it's 7.5 Earth years. It's only like 4.25 Mars years or something like that, that it's been there. So when we talk about these missions, we always refer to them in terms of Earth years. But an absolutely great question there, Tom. Melanier wants to know, how heavy is the payload? The solar orbiter weighs roughly 1,700 kilograms, which is pretty light. It's not a big probe. It's very, very small. But it takes a powerful rocket like the Atlas V to get it where it's going today, because if this were just going into low Earth orbit, the Atlas with a single solid rocket booster would be immense overkill for this mission. But even though it's lightweight compared to a lot of other probes that have launched, it requires a very powerful launch vehicle. All right, so keeping on with the questions here, and if you've got them, keep throwing them up. Again, if you're just joining us, I'm Chris Gebhardt, the Assistant Managing Editor of NASA Spaceflight. We are about, it's 22:27 here.
35 minutes.
So we're about 35 minutes away from an anticipated liftoff time. The Atlas V will so there is a built-in hold coming up in this countdown. We should actually be in it now, or very close to it. Can you go check what the countdown clock says for me? 40 minutes. Oh, so we're 40 minutes away from liftoff, and we're, what's the countdown?
T-minus 20.
T-minus 20 minutes. So there is a built-in hold at the T-minus 4-minute mark in this countdown. This is planned. It is built in, so when you see the countdown clock stop, don't panic. It's normal. United Launch Alliance has a built-in hold at T-minus 4 minutes so that if they're behind in anything, they have some time to catch up. But it's also when they do their final go, no-go poll for launch to verify that everything is ready before the 4-minute terminal count begins until liftoff. So if you have questions, keep throwing them up, because this should be an absolutely gorgeous launch. But right now, they're not working any technical issues. They're not worried about the weather. There's nothing right now that would prevent an on-time liftoff at 23:03 Eastern, which is 4:03 UTC and 5:03 Central European Standard Time. And I'm going to keep saying Central European Standard Time because that is the time zone that the missions control center for Solar Probe is located in Germany. So that's why I'm going to keep referring to that time zone as well. So Catherine Lee, I hope I said your first name correctly. When will we see the Atlas V fly with the GEM 63 solid rocket? So that's an excellent question. So the solid rocket boosters on this, or the solid rocket boosters used on Atlas right now, are built by Aerojet Rocketdyne. But United Launch Alliance will be switching them out for Northrop Grumman produced GEM 63 solid rocket boosters. We don't have a specific date or a specific mission for that yet, and part of that we understand has to do with the Atlas V's role in the commercial crew program with Starliner, but that change is coming. But ULA and Northrop Grumman have not given us a date yet or a mission in which that will happen. And oh my God, NASA has just begun blaring something. I don't know if you can hear that. I hope you can't. But very, very interesting. So Frank wants to know. So Frank was asking about the imbalance of thrust, and Frank, I hope we answered your question earlier there about how the RD-180 gimbals to compensate for that for that single solid rocket booster there. Dovorans wants to know, why is the nose cone of the Atlas V conical? Do cones have fairly poor drag? Don't cones have fairly poor drag, especially in the transonic region? So the region the payload fairing is so pointed on the Atlas V has to do with how, when the air flows over the payload fairing, how does it flow over the rest of the rocket, right, in flight? And because of the way the Atlas is built, with the smaller Centaur upper stage that widens out into the Atlas V, and how the Atlas V also has to fly sometimes with solid rocket boosters, that is the most efficient. That's the most efficient shape to ensure that the aerodynamics downrange or down the Atlas are maintained in such a way that they don't actually shake or vibrate the rocket to the point where it would fail. And Thomas, this actually goes back to something that they had to add to Atlas V for Starliner.
Sure. Yeah, Starliner had to have an extra piece of aerodynamic equipment called an aeroskirt on the bottom of the Starliner crew spacecraft. Because of the aerodynamics of that kind of vehicle. It's very different from the payload fairings that you would normally see on these types of missions. And again, this is all to reduce the stresses that the vehicle experiences as it goes through, especially the maximum aerodynamic pressure, or max Q area of flight. And during those regions, it's very important to make sure that the vehicle is stable and isn't going to shake itself apart through vibration. Excuse me. So yeah, that's one of the many factors that goes into which kind of aerodynamic surfaces each rocket has.
Yeah. Oh, and Elizabeth A., thank you for the super chat. We super appreciate it. Oh, sometimes words fail this late at night when you've been up since 6 a.m. for all the other stuff that's been going on today. Apologies for, you can kind of hear the NASA feed sometimes in the background, although it looks like they may have just turned off the audio on that. Apologies. We're actually standing right behind the countdown clock, or the multi-digital display device that's also a clock now. And it started speaking at us quite unexpectedly, and it hasn't done that on past missions, but it sounds like they've turned that off now. So anyway, Elizabeth A., thank you so much for the support in Super Chat. We really do appreciate it. This is our passion. We love doing this. We love bringing you all of these and bringing you up close. Like, we hope you guys really enjoyed the pad tour earlier today, as I was running around following Mike and Thomas around and everything. We like to bring you guys up close. We like to let you see what we see and experience. I think that's part of the fun of this, because it's really inexplicable about what it feels like to stand so close to something that is leaving the planet. And we hope that this brings all of you a little bit closer and convinces you that it's definitely worth, if you're ever near a spaceport, and to me, it doesn't matter what spaceport. If you're close to Kourou, if you're close to the Cape, if you're close to Vandenberg, or the Mahia Peninsula in New Zealand, or Baikonur, or any of the launch sites around the world, it is so worth it to get close to a rocket as it launches, because it's really an indescribable feeling as it goes, especially when it's a full moon. It's a full moon tonight. I mean, I can't think of a more perfect night for this to happen. Thank you so much. Yeah.
United Launch Alliance has just confirmed that the board is green. All weather conditions are green. We are all on track for an on-time liftoff at the opening of tonight's window at 11:03 p.m.
Yes!
Eastern. All is proceeding very nominally.
And that is exactly what we want to hear. Oh, hey, someone called SpaceX, I'm going to assume that's not actually SpaceX, wants to know, how did they come up with the idea to cover the heat shield with oh, never mind. So David Neal, are the center of mass and the aerodynamic center in line with each other? The aerodynamic center. David, if you're still on the stream, can you throw up a little explanation of what you mean? I'm not entirely sure what you mean by that, so I'm not entirely sure how to answer that.
If you're talking about the center of thrust and the center of mass, we did kind of touched on that earlier. Basically, they are roughly in line with one another, but especially when you have an asymmetrical thrust from the SRB, the center of mass moves as fuel depletes, and thus they can, become a little out of line, and the engines gibble to help counteract that. So roughly, yes, but for a unique configuration like this, not always, and there's some engine gimbal and counteracting that has to accommodate for that.
Definitely. Okay, and if you happen to mean the center of drag, like how the aerodynamic drag affects the vehicle, there is definitely more drag on the side with the solid rocket booster, because it's this big thing that just sticks out from the side of the vehicle. So that's also something that the RD-180 has to compensate for, that the unsymmetrical drag on the vehicle as it goes up. If either of those two answers are not what you meant, let us know, and that'll be passed along to me too. And hey, for Super Chat 2, Greg Smith, thanks so much for the $5. Again, really appreciate the support that you guys offer to us as we bring you up close to all of this really cool and awesome stuff that happens in the world of spaceflight. I know Das is in my ear on our ComNet, and Das is at Wallops. He was there for the scrub of the Antares mission today, and we found out just before we came on air that Antares' next launch attempt is not until Thursday, the 13th of February at 16:05 Eastern, which would be 21:05 UTC. They had a ground issue on the propellant side of things, a sensor giving them a suspect reading that they didn't like. So they've stood down to go fix that. And of course, the weather at Wallops doesn't look great on Monday or Tuesday with 80% no-go odds. So, but Das, a major shout out to you, because I know you're 800 miles north of us at another launch site. We were hoping for a doubleheader today, but I think that stream was still pretty fun. But here for Atlas, now, as Thomas just said, everything is looking good. There are no technical issues. There are no weather-related issues. So at this point, the countdown is just continuing. We'll hold at T-minus 4 minutes. They'll do their poll, but nothing would prevent us from launching at the opening of the window at 23:03 Eastern in the United States, which is 04:03 UTC. Darian Hernandez, thanks again for this for the super chat as well. DYU89, thank you to you too. And Greg, you had a question too with your super chat. How far are you guys from the Atlas V? Great question. We are 5 miles away. 5 miles. Oh gosh, Atlas V and 5 miles. As I told you, I am so sorry. I've been up since 6 a.m. and sleep deprived for the last 3 days between Solar Orbiter and Starliner and remote camera setup and rollout and Antares and now this and everything. So sorry, that was a slip of the tongue. We are 3 miles away from the Atlas V on its launch pad here. We are actually standing at the Kennedy Space Center press site right by the flagpole and the countdown clock, So if you're looking at if they're showing it live on screen, just look to the immediate right of the countdown clock where the 2 people right there, or the 3 people right there. It's myself, Thomas, and Nathan getting ready to photograph this mission as well. But yeah, we're really close, and it's exciting because when you're this close, you can actually, the sound doesn't have time to come together, right? From the ignition of the RD-180 and the ignition of the solid rocket booster, they don't have time to blend into one. So from our vantage point, we actually get to hear the deep rumbling groan of the ignition of the RD-180 and then the bang, the instant sound and vibration of the solid rocket. And what's really cool at this distance with solid rockets, and even the Falcon 9 does this with just 9 liquid-fueled Merlin engines, the thrust and the pressure waves through the atmosphere are so intense that you can actually feel the air rattling in your lungs. It's so cool. And if the rockets are powerful enough, Atlas and Falcon aren't really powerful enough this close that you feel the ground shake, but the Falcon Heavy, the SLS rocket, you can actually feel the ground shaking and quaking under you as these things launch. It's absolutely incredible. Absolutely incredible. So we got another question here from Felice or Thelsi Gryphon. I hope I'm saying your name correctly. This person has a question about navigation. Does it use some sort of digital camera sextant to get its location? I know Apollo did that. It's a great question. So this mission actually navigates a couple different ways. The cameras on board that are looking at the sun and monitoring the solar wind and the radiation particles and everything help provide some of that navigation lock, knowing where it is in relation to the sun, which comes in really, really important when it has to precisely aim its heat shield at the sun and be rotating itself in relation to the sun as it swings through its perihelion science dives. But it also knows where it is through radio communication with Earth, because we know exactly where Earth is, in relation to the solar system, in relation to the stars, the fixed stars that we use for navigation. And it can figure, and between those two systems, we know exactly where it is, and it knows exactly where it is. And of course, we're also in the age where its onboard computers know where it should be and can validate, and don't actually need star fixes or star locks to get that information, because and that's actually how a lot of our spacecraft navigate now. The Space Shuttle had a star tracker to help it navigate, but Starliner and Dragon don't have, those crew vehicles don't have star trackers. They know where they are from their software, from where the rocket drops them off, where they're going, and their communication with the ground. And that's exactly how Solar Orbiter will do it as well, with also the benefit of using our star, our parent star, to see that.
So they just cut out T-minus 6 minutes, which is 2 minutes away from the T-minus 4
And they just had some kind of technical issue, Michael is telling me. Did they say what it was, Michael? Okay, hang on one second for us, guys. We're going to go listen to the net and see what's going on. Stand by and stay with us. Okay, so what they are saying over the net is that the red line monitor, which is the part of the Atlas system that detects anomalies and out of family values for the various parameters that it monitors, that something went out of a prescribed limit. They are talking about it on the anomaly net. This sounds really scary and really intense. But this is very normal for United Launch Alliance. When there is anything that goes out of limit, they go talk about it on the anomaly channel, and then they come back and do a briefing and explain what it was and give a recommendation. It could be anything from, one particular sensor is malfunctioning, and they can just discount that and eliminate it from the red line monitor and from how the vehicle monitors it, to something a bit more serious. We don't know yet. But something did go out of limits. We haven't heard what yet. And Michael, if you're hearing anything too on what that might be, let us know. But if you are just joining our broadcast, we are live here at the Kennedy Space Center. You are looking live at the Atlas V on Space Launch Complex 41. It is fully fueled at this point with RP-1 rocket-grade kerosene and liquid oxygen in the Atlas booster, and with liquid oxygen and liquid hydrogen in the single-engine Centaur upper stage. Again, there has been some kind of an anomaly that was called out over the over the launch net. Here, they have not yet said what that is. Again, don't panic. We listen to these nets and these comm nets all the time. There are always minor little things that tend to come up that are dispositioned. Some of them can be more serious. We don't know yet. So there's no need, there's no cause for alarm. There's no need to panic at this point. And we'll just simply wait to hear what it is. Hold on, they might be talking about it. Hang on. Okay, and they have just briefed out that the red line limit had to do with the liquid oxygen storage tank, which they have been seeing issues with. It is not required for launch today. There is no anomaly. There is nothing with that would prevent them from launching tonight. So this is one of those things where I say don't panic, because these little things pop up all the time. But one thing about the Atlas V and United Launch Alliance campaigns is that their launch team is very talkative. They really talk everything out over the net with each other. So like we said, just because there was a red line monitor that tripped on a particular issue, this turned out to not be anything that is a violation of flight rules, and something that they knew was an issue earlier in the day and proceeded anyway. It just flagged in the system when it was doing its normal checks to make sure everything was ready, but it was a locked storage tank issue that is not required for flight. So there is no violation of our flight rules or our launch commit criteria at this time. So at this point, there are no technical issues, there are no weather issues that would prevent an on-time liftoff at 23:03, which is about 13 minutes from now. Woohoo! And I think, boy, do we need a launch tonight.
Yes.
It would be a good night, right? February 9th, that feels like a good day to launch to the sun.
It's a good day to go to space.
I mean, it's still sun day here at the Kennedy Space Center, so I think that's a good day to launch to the sun, right? Yeah. If you do have any questions, continue to throw them up in chat. Even if you joined us late and you think your question might have been answered before, go ahead and throw it up there. We'll re-ask it. They'll send it to me. My team will send it to me. And we'll re-answer it, because I bet you're not the only person who hasn't been watching since the very beginning of the stream. I bet you're not the only person who still has this question. So let us know, and we'll get it re-answered. But we are about 13 minutes away from the opening of our launch window, and there's nothing at this point that would prevent an on-time liftoff of the Atlas V. At this point, Thomas, do you want to take it away for a couple minutes? I want to ask Michael something. I just want to step away, but it's a gorgeous night.
Yes.
And this is and earlier today was your first day actually at the Atlas pad.
Yes.
Talk a little bit about that too.
Yeah, sure. A brief update. They have confirmed that winds are confirmed green for the entirety of the 2-hour launch window tonight. So that's another weather condition that is completely green. And like we said, that minor LOX tank issue has been resolved. Therefore, all systems are green, all weather criteria are green, and the range is green for launch right now. All systems are go for tonight's launch. And yeah, like Chris mentioned, this is my first Atlas V launch, and I'm looking forward to it. My first visit to Pad 41 earlier today. And after that, I will have seen all 3 major rocket families, Falcon, Atlas, and Delta, over on the East Coast here. But yeah, this is a unique Atlas V 411 configuration if you are just joining us, launching the ESA's Solar Orbiter mission. And all systems are on track for an 11:03 p.m. Eastern or 04:03 UTC liftoff from Pad 41 at Cape Canaveral Air Force Station in Florida.
Okay, perfect. Okay, cool. Thank you, copy that. So yeah, it's been a day, hasn't it? Yeah. It's been a day already, but So the next thing, the major thing we are standing by for 7 minutes before our anticipated launch in the T-minus 4 minute hold, which we are in right now. We're at T-minus 4 minutes in holding, which is a scheduled built-in hold that's totally normal for United Launch Alliance. About 7 minutes before our anticipated liftoff. So coming up here, probably within the next 6 minutes or so, we will have the final poll of all the stations. Go. They will do their go no go poll for liftoff. So as we're sitting here, there's one thing I wanted to kind of draw your guys' attention to. If you look to the right of the rocket and you see the two lightning towers there, and you see a little orange flame burning right there at the base of them, that is a fire. That is a flame. That is the hydrogen burn-off stack at the Atlas pad. So as the cryogenic hydrogen that they have loaded into the Centaur upper stage boils off, you can't just vent that into the atmosphere like you do the liquid, like you do the gaseous oxygen, which is the white vapor you see coming out about the middle of the Atlas V itself there on the pad, because hydrogen is very combustible, and you don't want to be releasing combustible elements into the air around your rocket that you are about to light gigantic controlled explosions in the engines and launch through. So the way they vent that liquid hydrogen that has boiled off is they vent it out of the rocket's second stage through a hydrogen vent line that is firmly secured and sealed so it doesn't leak. They vent it down the umbilical tower and then out to that flare stack where that they've ignited earlier in the day, and then they burn that gaseous hydrogen right there at the flare stack. So that's what you're seeing is the hydrogen that's boiled off and is being pumped out and is being vented away from the Centaur upper stage. You're seeing them burn that off, and when they burn it off, there's then nothing left in the ambient air that's combustible. And that's how we really protect rockets that use liquid hydrogen from any sort of massive fireball or combustion event on the launch pad, because we don't want that, right? There's always a little bit of gaseous hydrogen around, but there are limits that are acceptable and limits that are not, that they can't cross, and there's no need for that today. But you can't really see the hydrogen flare stacks during the day, so I wanted to point that out to you all, because it's a really, really cool thing when the alignment is perfect and you can see it. So yes, so Nelson, thanks for the super chat support there. We really do appreciate it. We hope you're enjoying from wherever you're watching around the world. We really hope you're enjoying this. This should be an absolutely epic launch coming up here in about 10.5 minutes. So we should be getting close, about 3 minutes away from that poll, just to verify that everything is good to go here. So we do have a couple more questions to get through here. Why do I keep reading that this launch is going to power slide off the pad? Well, you're reading that because it's a really, really cool component of the Atlas 411 configuration. That single solid rocket booster that is mounted on one side of the rocket creates so much asymmetrical thrust that it will push the rocket to the south as it lifts off the pad. So from our vantage point here, it will not rise vertically. It will actually push to the right of the screen as it's coming off the launch pad. And that's what we refer to as the power slide maneuver in the initial seconds after liftoff. What were they saying there, Thomas?
10 minutes before launch, they're getting ready for the final poll.
Cool. And all the things are live, so we can bring the net closer or turn up the volume so people can hear the poll. That's a good thing. They should be able to hear the poll and everything. So yeah, so that's why you keep reading about the power slide. Another question we have is the solar orbiter going to talk to the Deep Space Network or a satellite in between the Earth and the Sun? Great question. It's actually not going to talk to either. It's going to talk to a receiving dish in Germany near the spacecraft control center. That's the primary dish that that solar orbiter will connect down to and communicate with and do all of its science downlink through as well. It's possible that it could also talk through the Deep Space Network as well, but the primary communication will be through this dish in Germany. But a great question there for how it's going to do. So we are very, very close to launch. We're very, very close to this pole. I know Nathan's ready with at least 3 cameras, including one that he hopes will work. That should be an epic streak that will really show you that power slide that we've been talking about here. So I'm going to stop talking for just a minute here. I need to configure the camera on my end so that it maintains its focus on the Atlas as it climbs. So I'm going to stop talking for just a minute, but stay with us here, and we will be back to bring you that poll. Actually, Thomas, if you want to just leave that here, we're going to let you listen into the countdown net while I reconfigure the camera here.
Yes, and they just confirmed that all steps prior to the final go no go poll have been completed, so we're getting really close to that final go no go poll.
Yeah, Das, what do I need to do with that again? Okay, copy that, Das. Okay, sorry, just to confirm, manual focus and auto exposure? Okay, perfect, thank you.
Status check to proceed with terminal count. Atlas systems, propulsion. Go. Hydraulic. Go. Pneumatics. Go. LO2. Go. Water. Go. Centaur systems, propulsion. Go. Pneumatics. Go. LO2. Go. H2. Go. ASGAT. Go. Electrical systems, airborne. Go. Ground. Go. Facility. Go. RFFTS. Go. Flight control. Go. GCQ. Go. Operations support. Go. Com. Go. Umbilicals. Go. BCS. Go. Redline monitor. Go. Quality. Go. Op safety manager. Go. Relay safety. Go. Vehicle system. Go. Anomaly chief. Go. Range coordinator. Clear to proceed. Launch director. You have permission to launch. Proceeding with the count. ALC, verify T0 is set for 04030. Verified.
And you just heard all systems are go for tonight's launch at 11:03 p.m. Eastern.
Amazing! So this is the part where I can't control the inner kid in me because rocket launches are just phenomenal. This is the part where I get really, really giddy and really excited, but then also super nervous because the rocket is ready. But there's still a lot to do, right? At the final 4 minutes, we will see the pressurization of the
Verify spacecraft is configured for launch.
Verified.
So solar orbiter is configured for launch, but this is the part of the countdown where
configured for launch.
where you do start to get just a little bit nervous because this is the point where you now have to pressurize all of the propellant tanks in the Centaur and the Atlas. You have a whole bunch of systems that are activating on board the rocket. Some systems that have not been activated yet, right? So, and of course, anytime you actually light a rocket engine is a huge deal. So we're very happy. We're excited to see this mission go. But, this is the point where I always have to step back in my head and remind myself that as excited as I am, this is still a this is still a rocket launch. This is still an incredibly complex vehicle and an incredibly complex mission that's about to unfold with very little room for error. The United Launch Alliance are champions at this. The Atlas is an amazing vehicle, but you always have to remain grounded at this point in the countdown. But if you are just joining us for launch,
on my mark, time will be T-minus 4 minutes and counting. 3, 2, 1, mark.
We are at T-minus 4 minutes and counting to the launch of the European Space Agency's solar orbiter on the Atlas V 411 rocket from Launch Complex 41 at the Cape Canaveral Air Force Station. This will be United Launch Alliance's first launch of the year. They have a very busy schedule coming up this year. Some of the highlights include the Advanced Extremely High Frequency 6 satellite, the next flight of the U.S. Air Force's X-37B space plane, and the crowning achievement this year, most likely for the Atlas, the launch of the Mars 2020 rover in July, Curiosity's cousin. But a busy and exciting year ahead for United Launch Alliance. This is their first launch of the year with the Atlas V. And go ahead and keep that close to the...
T-minus 3 minutes.
Securing yellow topic.
Atlas takes the flight pressure.
So the Atlas booster tanks are being pressurized for flight.
2 minutes, 50
and
seconds.
they have stopped replenish of the liquid oxygen
That's
into
it.
the Centaur upper stage at this time. The next thing they will do is secure Centaur LH2, which will be stopping liquid hydrogen replenish to the Centaur. And at that point, the vehicle will be isolated from all fuel loading equipment, and the fuel lines at the pad will be purged with gaseous nitrogen to inert them and make them safe for the ignition of the Atlas, when the RD-180 will light at 2.7 seconds prior to liftoff, and the solid rocket booster will ignite at T0, and we will have a fairly rapid liftoff of the Atlas V from its launch pad.
$159. 155. Launch sequencer start.
The automatic launch sequencer has started.
150.
Securing Centaur LH2. Securing Centaur LH2.
So that completes isolation of the vehicle from its fuel loading equipment. And what you
40.
heard, the sequencer start,
Launch
that
enabled.
means that the Atlas V
37.
itself has control of the countdown at this point.
FTS on.
That's the flight termination system, which is manual for the Atlas V. Rocket, of course, we hope to never have to use that, but all
120.
U.S. rockets have a flight termination system
OCUs
so
on.
that if anything should go wrong, we can destroy them to
150.
protect land, sea, and air assets.
110. T-minus 1 minute.
Rock, report range status.
Range green.
Range is green. That's what we want to hear. That means the eastern range here in Florida is go with no technical issues.
T-minus 40 seconds.
Able to step through.
Here we go.
28 seconds. 25.
Status check. Go Atlas. Go boost Centaur. Go solo orbiter.
15 seconds and counting. 7, 6, 5, 4, 3, 2, 1. RD ignition. Solid ignition and liftoff! Yeah, baby! Go, 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 go! Look at that! Power slide, baby!
The tower. Now beginning the pitch over maneuver.
Go,
Body
go,
rate response
go.
is good. Seeing good engine operating parameters on the RD-180 engine. Now passing 15 seconds. Atlas propellant utilization system is going to closed loop control. System response looks good.
Everything nominal in the first few seconds of flight. Listen to that rumble, baby! Go, baby!
5 seconds into flight. Check the pressure on the SRB looks good. Engine operating parameters on the RD-180 also look good. And 35 seconds here. The vehicle is completing the pitch over maneuver. Now 5 seconds into flight. RD-180 throttling down slightly as expected, and the engine response looks good.
Look at that.
And vehicle now passing 1 Atlas V is now supersonic.
Gorgeous, gorgeous! Oh, come on, it might go right over the moon. Come on!
Vehicle's now passing through max Q, maximum dynamic pressure.
Come on.
RD-180 continues to look good. Pump speeds and injector pressures look good. S3 chamber pressure also looks good. Vehicle's throttled back up to full thrust as expected.
Full thrust. Look how close to the moon it is. Oh, I just missed it.
And standing by for SRB burnout.
All right, we are standing by for solid rocket booster burnout. Absolutely flawless
And we have
flight
burnout
so
on the
far.
solid rocket booster. Atlas will hold on to the SRB for an additional 47 seconds prior to jettison. Now 1 minute 45 seconds into flight. The 180 continues to perform well at full thrust. Pump speeds and injector pressures look good. And now coming up on 2 minutes into flight, the Atlas V vehicle now weighs just 1/2 of its liftoff weight. RD-180 throttling down slightly as expected. Engine response continues to look good. And standing by for SRB jettison shortly. And we have good indication of jettison of the solid rocket booster.
Woo!
Atlas V has gone to Q alpha limited loop steering.
Look at that. You
Vehicle
can
body rates
actually,
look good.
so you can see the solid rocket flipping away there, that orange dot, but you can
Now 2
also
minutes,
see
35 seconds into flight.
the white contrail is actually being illuminated by the full moon. That is freaking awesome. By a star. Awesome, awesome, awesome. Come on, baby.
And the second stage RCS system press valve is opened. System now pressurizing to flight levels. Now 3 minutes into flight, approximately 1 minute remaining until BECO.
So BECO is booster engine cutoff. That is when the Atlas
180
core.
continues to look good. Pump speeds and injector pressures look good.
So that is the Atlas core booster, which has about a
3
minute
minutes,
left. So
15
that's
seconds in.
booster engine cutoff when the RD-180 will shut down prior to
Vehicle body rates
separation
look stable.
of the Atlas booster from the Centaur upper stage and ignition of the RL-10 4A engine.
Now 3 minutes 30 seconds in. RD-180 now throttling to maintain a constant 5G acceleration limit. Engine response looks good.
Holy crap. Come on, baby.
And we've begun boost phase chill down.
Look
Now
at that.
throttling
Look at
to
that.
a
Tom,
4.6G
look at this.
acceleration limit. Boost chill down has ended. Standing by for BECO.
Look at that starburst coming off of the RD-180. Oh, engine cut off.
And we have BECO booster engine cutoff. Standing by for stage SEP.
All right, standing by for stage SEP. There we go.
And we have good indication of Atlas Centaur separation. We have pre-start on the RL-10. Standing by for ignition.
Come on. What you saw there were the thrusters on the Atlas
We
firing
have
to separate
ignition
it. There it
and
is.
thrust on the RL-10. Chamber pressure looks good. Body rates look good.
There it is. Oh my God.
And we have good indication of payload fairing jettison.
Payload fairing jettison 2. Yes.
This first burn of today's mission will last approximately 8 minutes.
So we have had a successful first stage flight of the Atlas V rocket and separation of the sequence. That flash you saw right before the RL-10 ignited were the symmetrical thrusters on the Atlas booster that fire to separate it away cleanly from the Centaur upper stage. That was absolutely amazing. I've never seen that flash before from the ground. We had a good ignition of the Centaur, the single engine Centaur upper stage that is now burning to take Solar Orbiter into its initial parking orbit of Earth. This is a 236 by 203 kilometer orbit where it will perform about a 30-minute coast before reaching the point in that orbit where it will reignite to begin the Earth escape burn. And there it goes behind a cloud. Whew! That was absolutely gorgeous.
And RCS system now
Here.
periodic firing for thermal conditions of the system. System response looks good.
Okay, so what you are now looking at is animation provided by United Launch Alliance on NASA television of what is happening.
Initial review of booster performance shows the booster performed close to pre-flight predictions.
Which is awesome. So that call out that you just heard about booster performance near expectation is United Launch Alliance's way of saying perfect performance of the Atlas booster and the RL10 and the RD180 engine. Nathan is showing me a streak shot that he got, no editing, and oh my god, it looks amazing. Especially with the moon right there at the apex of the arc. Oh so man, that was so...
Centaur has performed a roll to optimized telemetry link.
Good.
Chamber pressure continues to look good on the RL10.
So they're already 187 kilometers in altitude right now.
Good control on the Centaur propellant utilization system.
And Centaur actually communicates upward to satellites in orbit. So what you heard there,
45 seconds into flight.
So what you heard there was that the Centaur performs a roll maneuver to optimize that communication. If you ever watched a space shuttle mission in the post-Columbia era, the onboard cameras on the external tank, you would see the shuttle about 5.5 minutes after launch perform a roll to a heads-up maneuver to improve communication with the tracking and data satellite relay network, which is exactly what Centaur communicates to. So Centaur just did a very similar roll to a heads-up position to maintain good communication with the tracking and data satellite relay network.
And the Centaur telemetry format has changed to the TDRS compatible format.
There you go.
I did see a minor dropout in telemetry, but have regained telemetry and quality looks good.
Okay. So a momentary drop in communication as it made the handover from ground stations to the TDRS network as expected.
Continue to see good control on the propellant utilization system, periodic firings on the RCS motors as expected. And we are seeing RCS line temperatures approaching bottle temperatures as expected.
So it's really easy to get super excited right now here because from our vantage point, the rocket is out of view, but we don't breathe easy yet. The RL-10 engine is still firing. The Centaur is still doing its job to get the rocket into its initial parking orbit. We still can't breathe easy once it's there because it still has to coast and then reignite that engine for the burn into Earth escape heliocentric orbit.
4 minutes remaining in the burn.
Yeah. So what you're seeing on the screen right now is a positive apogee but a negative perigee. So apogee is the highest point in the orbit. Perigee is the lowest point in the orbit. Right now, perigee is still underneath the ground of Earth. So if the engine were to cut off right now, Solar Orbiter would re-enter the atmosphere and crash into the ocean, burn up and crash into the ocean. So when you see that perigee indicator on the telemetry go positive, right? Positive is good, but we need that positive mark to be above 121 kilometers, which is where Earth's atmosphere really begins for re-entry. And we want that perigee to end up saying 203 kilometers. That's what we want it to say at engine cutoff. So you have an apogee of 286 and a perigee of 203. And Brady is walking toward me with a gigantic smile on his face, so he's got an awesome freaking photo to show us too that we'll be able to share with you later. Oh my gosh, that is amazing. He is showing me a slow-mo video of it coming off the pad. Epic.
It's gonna be awesome.
Epic. We're gonna have a lot of really cool video and awesome photos to show you, but before we get ahead of ourselves, there's still good telemetry, still good data. All data points are still indicating a nominal flight of the Centaur. About 2 minutes, minute and a half, 2 minutes left in this burn. It's really easy again to get excited, but you know, the business part of this is still really taking place right now. So
10 minutes into flight. Centaur is 145 miles in altitude.
And that's a photograph that Brady got of the liftoff.
15,700 miles per hour. Now 2 minutes remaining in the burn.
Okay, so 2 minutes remaining in our burn. So that perigee is still negative, and that perigee
operating parameters continue to look good throughout this burn.
And that
propellant utilization system is continuing active control as expected.
Cool. And I'm trying hard not to talk over what they're saying on the net so you can hear it too. But that perigee is still negative, and that's normal right now. That perigee will not go positive until the final couple of seconds in the burn. So much of getting a rocket to orbit is not getting the apogee high, it's literally taking the perigee from the center core of the Earth and having to lift it thousands of kilometers out of the Earth and get it above the atmosphere, and that takes a tremendous amount of energy
And we are seeing
to do.
stable value on
So
helium
that
and
will
hydrogen
be
storage
negative
bottle
for
pressures,
that will be negative until
as well
the
as
final seconds
LOX
there.
and LH2 tank pressures look very stable throughout this burn.
I mean, everything we're hearing is a
Just under
very
1 minute now remaining in the burn.
about a minute remaining. Everything we're hearing indicating a completely nominal burn and performance of the Centaur engine, the Centaur upper stage,
11 minutes, 30 seconds into flight.
and its RL-10 engine. We are standing by now for SECO-1, which stands for Stage Engine Cutoff 1. And the reason we call it 1 is because it will coast and then reignite and then shut down again. So
Just under 30 seconds now remaining until MECO.
Standing by for SECO-1. I think he just called it MECO, which stands for Main Engine Cutoff. Same thing, different terms for the exact same things.
And our body rates continue to look stable.
So I'm going to stop talking and we will
He's
wait
gone
that
to open
call.
loop in preparation for MECO. Standing by for MECO. And we have MECO, main engine cutoff.
Yep.
Body rates have damped out nicely from the shutdown transient.
So now we wait for nominal orbit insertion call.
And Centaur is now commanding 100% 4S settling on the RCS thrusters.
So now the NASA TV feed is delayed. That's on NASA's side, not on ours. So you're about to see that engine cutoff occur.
Centaur now turning to the desired passive thermal control roll attitude. Body responses look good.
We'll explain what that means in a minute. We're still waiting for that nominal orbit insertion call.
And this coast should last approximately 30 minutes.
Which that might be that might be their version of nominal orbit. There. But anyway, what Centaur now has to do is Centaur has to spin so that it maintains constant thermal conditions around itself. If it didn't spin, right, one side would receive more heat, more thermal energy than the other side, and you could get temperature imbalances inside the liquid hydrogen and liquid oxygen tanks, which you don't want because there's still propellant in there, and there's super cold cryogenic propellants that are gradually getting warmer. And you don't want huge temperature imbalances, so you have to roll the Centaur around its axis, around its velocity axis, so that it maintains proper temperature in those tanks. But all indications is that we've had a nominal orbit insertion of Centaur. It should be in a 286 by 203 kilometer parking orbit. It will now be coasting upward to the for about 30 minutes. And it will reignite that engine 42 minutes after liftoff. For fans of Hitchhiker's Guide to the Galaxy, a wonderfully coincidental number.
Now 14 minutes, 15 seconds into flight.
And
a brief review of the Centaur performance after the first burn shows all major orbital elements very close to pre-flight predictions on apogee, perigee, and inclination.
Yes! So that is confirmation of a good and successful orbit insertion. Again, ULA doesn't say perfect, they say near predicted values because you're aiming for 286 by 203. But if you get 286.1 by 202.9, you've hit it. Right, like you've hit it basically on the mark and done the bullseye, even though those numbers might not be exactly rounded to the 0 decimal. But that's true of all rockets, right? So ULA
and passing 15 minutes into flight, Centaur body rates indicate the vehicle is continuing its turn to the PTC attitude.
We can know that now. So a successful first part of our flight here, but we are now in a 30-minute coast phase before that engine will reignite. They're showing that what you're seeing right now is the schedule of events and when they will occur. The Centaur engine reignition, when it will shut down. When it's shut down, that's when it's in its that's the completion of the Earth escape burn to heliocentric orbit, and then solar orbiter will separate shortly thereafter, going at a velocity of 12.03 kilometers per second. For comparison, the International Space Station orbits at 7.8 kilometers per second. So much, much faster than the International Space Station is going. But a very successful first part of our launch. The solid rocket booster did its job perfectly. The Atlas booster functioned absolutely perfectly. The Centaur has functioned perfectly and is now in its coast. So now we just wait for that final burn and spacecraft separation, and solar orbiter will be on its way. We absolutely do not want to call anything yet because the mission is not done. So while we are in this 30-minute coast phase, if you have any questions for us, we're going to remain on. We're going to remain on the air here with you. Michael, if you could switch it back to the feed from my camera, I want to show them Slick 41 here and what it looks like after liftoff, and go through a few things as we're in this coast. But if you have any questions about this mission or anything regarding the pad, throw them up into the chat here, and we will continue to answer your questions here as we wait out this 30-minute coast phase. So what you are looking at right now is Slick 41, and aside from a missing rocket, looks pretty much the same. And the reason I wanted to show you this is because after the Starliner launch, right, after any launch with solid rocket booster, so Starliner back in December, solar orbiter right now, solid rockets are very, very acidic and very, very corrosive. So when they burn, you need to take precautions to protect your launch pad. Now, depending on the number of solids that there are, sometimes that means ULA instantly activates a water deluge at the pad to rinse off of that all of that corrosive aluminum that comes out of the solids. And sometimes they don't, and they haven't today because the single solid rocket is a different calculus for them. But you can still see part of the hang on here. You can still see part of the I'm sorry. You can still see part of these umbilical tower venting gaseous oxygen, which is normal because as all of the propellant lines that feed all the propellant into the Centaur, right, separate as the Atlas pulls away from the launch pad, right, you get these things that continue to vent. The pad really takes a beating from a rocket launch, and even though we won't be doing a live stream when we go back to the launch pad to get our remote cameras, we're going to record all of that live to a camera and upload it to our YouTube channel so you can see the condition of the launch pad after liftoff. It's very, very different condition than when we were there just this morning setting these cameras, and everything is still kind of pressurized, everything's still kind of breathing. The pad seems like it's alive when we're out there, so we're going to record that to definitely get that to you. So if you have any questions, go ahead and throw them up in chat and we will get them answered for you. And Nathan's showing me a picture. He got the power slide showing exactly how much the Atlas really translates to the south as it lifts off, and then as the engine begins to gimbal, how it wiggles back onto course. We've got a lot of cool video and photos to show you of this mission, some of which will be up soon. I think Brady already has a photo published. Go ahead, Michael. Perfect. And what you're going to see next is a photo that Nathan got of the liftoff sequence. You already saw one of Brady's. This is what Nathan got. And we also had Mike Deep here with us. He was not here with us on the ground. He was on top of the vehicle assembly building. So he's got some awesome photos and video coming as well. But we'll be posting that throughout the night and into tomorrow morning, local time here in Florida. But again, we are waiting here through a 30-minute coast phase. The Centaur will reignite its RL-10-4A engine 42 minutes after liftoff to start doing that Earth escape heliocentric orbit injection burn. So as we wait that out, if you've got any questions, let us know. I've answered all the questions that my team has sent to me through here, but if you can for my team on the background, if you can post the questions into the question queue in our Discord in the command center DOS. That's where I'm looking to see where they are. So if you're listening to this, if you're still watching with us as we await the final elements of the mission before we can declare mission success, go ahead and throw those questions up, and my team will send them to me. But again, when we started this live stream, we promised you that if you were bored with the Oscars, that United Launch Alliance and the European Space Agency and NASA would give us a much more exciting show. And boy, did they deliver! And actually, let's see if we can see this here, because I hope we're still on my camera here at the press site, because look at the difference that just 20 minutes makes. It was a crystal clear sky when Atlas V launched, and it is now almost completely overcast. A delay to the 23:23 instantaneous launch time, we would not have seen what we saw today. We wouldn't have been able to show you the absolutely incredible separation of. Oh, Nate just made an appearance there as he's collecting all of his tripods. But we wouldn't have been able to show you that separation of the Atlas booster, the flash of the thrusters as it separates because of the clouds. And that's the difference that 20 minutes in Florida can make. There's an old joke about the weather here in Florida that if you don't like it, wait 20 minutes, it'll change. Well, it does. So very happy we were able to bring you all of that. So as we continue to wait out this coast, the next flight of the Atlas rocket is scheduled for March, and it will launch the Advanced Extremely High Frequency 6 satellite for the U.S. Air Force. Not a classified mission for the U.S. Air Force, definitely not classified because we know what they look like. But that one will also be a rocket that has solid rocket boosters. This is the Beast. But this will launch on the Beast, the Atlas 551, a 5-meter payload fairing 5 solid rocket boosters and a single-engine Centaur upper stage. The next one after that will be a 541 with 4 solid rocket boosters, and the one after that will be a 541 to launch the Mars 2020 rover on its way to the red planet. Nate making another appearance there in the bottom of the screen. Now he's going to try to be real shady, so I'm going to turn the camera just to get him on there again.
Chris,
But yes, ULA has a wonderfully busy year coming up here. There's also a TDRS mission on their books coming up, either toward the end of this year or the beginning of next year. TDRS is NASA's tracking and data satellite relay network of satellites. The Atlas will be used to launch the next one of those on a 401 configuration with no solid rocket boosters. So a good variety, but this is definitely the year of the solids for Atlas. And if there does happen to be another Starliner launch this year, be it a reflight of OFT or the crew flight test, that will also use solids as well. So definitely the year of the solids for the Atlas.
lots of solids.
And I can remember, years where we would go years without a solid on an Atlas, and now we're just banging them out here one after another, which is awesome. So we do have a question. How big is the Atlas 5411 configuration compared to the Falcon 9? What do you mean? It depends on what you mean by big. If you mean in terms of power, the more solid, the Atlas V with no solid, with just this configuration of the 411 does not produce as much thrust at liftoff, or produces just slightly more thrust at liftoff than the Falcon 9 does. But if you mean in terms of size, they're fairly comparable in height to one another. I believe the Falcon 9 is slightly taller than the Atlas V, but if you're talking about thrust and performance, I believe the 411, because that solid produces quite a bit of thrust, is either just under or right around a Falcon 9, which produces 1.5 million pounds of thrust at liftoff. There, and yeah, Das, you were going to say something to me there as I started answering that question there. If you want to go ahead, I'm listening as I keep talking here. But yes, but don't go anywhere because guys, because we're staying live until the second burn. We're not going to leave you hanging here. We've got the NASA TV feed to put up, which we'll be cutting back and forth to, so you can see the animation, or if they have onboard cameras on the Centaur of what it's actually doing. So don't go anywhere. The launch isn't done yet. We're in a 30-minute coast phase. The reignition of that Centaur should happen at 23:45, which is about 14 minutes from now, or I'm sorry, 15 minutes from now. So don't go anywhere, because that burn is the one that will complete the launch portion of the phase and get us to the point where Solar Orbiter can successfully separate from the top of the Atlas. So right now in Earth parking orbit, and Thomas, if you want to join this conversation, if you're doing something, continue. But if you want to talk about this, because we keep talking about orbital velocity, right? And we keep talking about this Earth escape velocity that this second burn is going to do, increasing it to 12.03 kilometers per second. But that's not how fast it's going right now.
No.
So how fast is it going right now?
Okay, so right now it's
27 minutes into flight, approximately 16 minutes remaining in the coast.
Nope, 16 minutes remaining in the coast.
I was kind of hoping you would just read off the velocity, and that would make my question answer a lot easier. But no, so right now...
No shortcuts, Thomas.
they're basically in a low Earth orbit currently. If they didn't do another burn, their speed would be pretty close to what the International Space Station and other low Earth orbit satellites are at.
7.8 kilometers per second.
Right about there. And right now they're going to add all that extra velocity with the Earth escape burn, and that's what's going to send it on its way to Venus.
And here's the really cool thing, right? Is it took 12.5 minutes for the Atlas V to accelerate from 0 to 7.8 kilometers per second, right? And and at Atlas booster separation, right, it was doing about 4 kilometers per second. So the Centaur only increased that from about 4 kilometers per second to 7.8 kilometers per second, right? So the Centaur doubled that, but it took twice as long for the Centaur to double that. But now that it's going 7.8, it will increase from 7.8 to 12.03 much quicker.
Yes.
Because it is so much lighter at this point. It doesn't have as much propellant in it. The Solar Orbiter's a mass hasn't changed.
Right.
But the mass of Centaur has.
And the fairings have dropped off, so there's other weight shedded.
Right. And the reason this happens, right, is because it's not because they thrust the RL-10 at a higher thrust for this burn. It thrusts at the same 100% rating that it was doing during its burn to get it into its parking orbit. It's just the mass is so much lighter that thrust, that specific impulse, goes a lot farther when you have less mass.
Yes.
Yeah. And this goes back to one of the questions that was actually asked earlier on in our broadcast about how do you escape Earth's gravity, right? And it all comes down to velocity, right? But how much effort you have to impart, right, to get that velocity change is directly equal to what the power rating of your engine is and how much mass you're trying to move. So as the Centaur burns down almost to fuel depletion here and really lightens up, that engine gets more and more and more and more efficient as the burns continue.
Yes.
Yeah. Which gets us that, but let's go back and talk a little bit about the launch. And if you got any more questions, definitely throw them up in chat for us. We've got a question here. Oh, it's actually Das asking us a question here. Why does it look like there's still a rocket on the pad? Das, that's an excellent question. It's an optical illusion. No. It's because what we're looking at, right? So we're going to go from the left-hand side of the screen here. So the first thing you see as you progress from the left to the right of the screen are 2 lightning towers. And then you see a large gray tower that sort of has this bulbous shape to it. That's the crew access tower that's used for Starliner. And then you see these 2 little, symmetrical gray, they look white, but they're in reality gray. Because they're bathed in xenon lights right now, that's why they look white. But you see these 2 little gray slivers, and that's the Atlas's launch umbilical tower. So how they got all the umbilicals attached to the vehicle, where the vehicle was actually clamped to and mated to, that's what you're looking at. So from our vantage point before liftoff, the rocket was actually behind that. and rose up from behind it. But that's what you're seeing now, and that's why it looks like there's still a rocket on the pad, even though there isn't. But it's a great question, right? Because normally from our vantage points, it's very clear that the rocket has launched, except here from our viewing location at the Kennedy Space Center press site, it's unfortunately you're looking through the launch umbilical tower at the rocket if the rocket was there, but of course the rocket isn't at this point. It's doing its awesome. It's doing its coast right now before it reignites its engine here in about 12 minutes or so. A good question that we have here is, which launch pad are we looking at? We are looking at Launch Complex 41 on the Cape Canaveral Air Force Station. And it is still called the Cape Canaveral Air Force Station. The name has not changed yet. The Air Force has said that the Cape Canaveral and Patrick Air Force Base will both change names. The Cape will become the Cape Canaveral Space Force Station, and Patrick will become Patrick Space Force Base. But they will announce in the next 30 days when that name change will take place. So it's coming, but we don't know when yet. So that's why I'm going to keep saying Air Force Station, because it is still an Air Force Station right now. And this is right now the Atlas V launch pad. But it is being configured, and there's a lot of construction going on to add gigantic methane storage tanks at the pad, because next year, in 2021 at the earliest, it will become a multi-vehicle use launch pad where it will be used to launch the Atlas V, which we just saw launch tonight, and also be able to launch the Vulcan rocket that ULA is developing. And the Vulcan doesn't use kerosene and oxygen for its first stage. It will use methane and oxygen for its first stage. So lots of construction going on at this pad. It will be a multi-rocket launch pad, just like Launch Complex 39A is a multi-rocket launch pad with the Falcon 9 and Falcon Heavy. Launch Complex 39B is a multi-rocket launch pad with NASA's SLS rocket and Northrop Grumman's Omega rocket, which will launch from there as well. And then if you keep going down the row, SpaceX's Launch Complex 40 is a single rocket pad. 37B for the Delta is a single-use pad. And Blue Origin's pad that's under construction at Launch Complex 36 is a single rocket use pad for the New Glenn rocket. But they are talking now over the net that the Centaur upper stage is still doing its normal role. And Thomas, what were they saying there?
On the storage bottle pressures, as well as LOX and LH2 tank pressures.
Sounds like everything's continuing to go well.
Minor telemetry dropouts throughout this coast.
Okay, so
which would be expected, right, as it passes between the TDRS satellites and is handed off from one to the next.
Yeah, so basically United Launch Alliance has confirmed everything proceeding nominally at this time. We're getting close to about 10 minutes, just under 10 minutes, until that Centaur RL-10 engine will reignite and start sending Solar Orbiter on its interplanetary trajectory. While we're waiting for that to happen...
now indicating 9 minutes remaining in the coast.
There you go, 9 minutes until that coast will end and the engine will reignite. While we're waiting for that to happen, go back to what we were just talking about and how Launch Complex 41 has a lot of construction and a lot of changes coming. We actually discussed this earlier today. We had a live stream from Launch Complex 41,
which you can go to our YouTube channel and find for playback. It's only about 45 minutes long, and it's really cool because we followed around all the photographers.
Yes, and we talked about construction on the pad and a whole bunch of other things. So if you want to check out what it's like to be at Launch Complex 41 ahead of a launch like this, NASA Spaceflight on YouTube, check it out.
Very, very, very much so. And Michael's going to pull up an image here briefly, but he's going to send it to me too, because we want to talk briefly before the reignition of the Centaur about the various flybys of Earth and Venus that Solar Orbiter is going to do. But Michael's going to send me that graphic so that I know what I know what you're looking at, and can walk you through it here. But again, we're about 8 minutes now away from the reignition of the Centaur upper stage, everything going well on orbit. So definitely continue to stay with us here as we... Oh, okay, I can see the graphic now too. Which is awesome. So the graphic that you are looking at on your screen right now is the sequence of flybys that are going to happen here. Michael, if you could still send this to me in the question queue, which is what I'm looking at, so I can pull it up and make it a little bit larger. I'm having a little bit trouble reading it on the screen when I can't blow it up, or make it bigger here. But basically what you're looking at is the sequence of flybys that are going to happen both with Earth and but primarily with Venus, because Venus is how we're going to get this spacecraft closer to the sun, and get it into its primary science orbit. So a successful launch today from the Kennedy Space from the Cape Canaveral Air Force Station here. So its first gravity assist maneuver that it will do with Venus will come on the 26th of December, 2020. So it's got a long way to go before it gets to Venus for the first time. So it'll do that first gravity assist maneuver on the 26th. We'll have another one then in August of 2021. And then after it does those first two gravity assists of Venus, that's when it will come back by Earth, and it'll do another gravity assist from Earth to change that orbit before it as it really starts to shrink down its orbit. But its first close approach to the sun at just 0.5 astronomical units will come in February of 2021. So about exactly a year from now, actually, after it does its first Venus gravity assist. But you can really see how that's going to happen, and how each progressive polar pass there, if you look at the top, right, from March of 2025 down to July of 2029, how the orbital inclination in relation to the solar equator really changes and gets us our first ever view of the poles. I mean, you can also see how many millions of kilometers it's expected to go through, about 300 million kilometers, 22 orbits of the sun, and the actual start of the main mission, because we launched today, will occur in November of 2021, so about 2 years to get to its primary science orbit, before it starts that 5-year primary science mission. And then, of course, once we reach December of 2016, we can potentially extend that mission outward to 2030 if the spacecraft is still functioning as intended, and it definitely has enough propellant on board to account for that extra to account for the potential extension of that mission. So absolutely great there. And so what's happening now in orbit, if we can switch back to that animation, is Centaur is now firing its thrusters to position itself for the upcoming burn that will inject Solar Orbiter into its heliocentric orbit and send it on its way to Venus. Oh my God, shooting star! Something just entered the atmosphere over there. Oh, that was really cool. A shooting star just literally streaked above Slick 41 and 40 as something re-entered the atmosphere, or entered the atmosphere. That was so cool to see. Oh, I'm never looking right in the right direction. That's so cool. Sorry, my excitement there. We do have a question. I think we've got time to answer it before we get to the Centaur ignition. Devorans wants to know, when launches fail, where are they most likely to fail? There is no actual answer to that. There is no more likely to fail at this period of flight than another, because it really just comes down to how they fail. Like, for example, earlier today, when Iran went to launch, they had a quote-unquote successful launch in that, like, all 3 stages of the rocket worked, but it didn't put the vehicle into the right orbit. Basically, they were aiming for a 546 kilometer orbit, but the rocket did something wrong, and the apogee, the highest point, did reach 546 kilometers, but the perigee never came out of the Earth. So it just came slamming back down into the Indian Ocean at orbital velocity, but the rocket just didn't pitch the right way. So, that was a launch failure based on the rocket not orienting itself correctly we've seen rockets fail because the engines explode, the turbopumps explode, the chambers explode. One of the more interesting launch failures came from Russia when they put half of the gravity sensors on upside down, so half the rocket thought it was upside down and half the Proton thought it was the right way up, and it just kind of wiggled and spun and then nosedived into the ground. But we've also seen Soyuz launches fail on the second stage. We've seen Soyuzes fail at booster separation. We've seen rockets fail on the launch pad. There's really no, if they're going to fail, there's there's really
most likely point.
Yeah, there's really no most likely point. Yeah. So nerds, I have it. The official to the uber millisecond liftoff time. Liftoff time of Solar Orbiter was 23:03 and 0.155 seconds Eastern Time off of Launch Complex 41. I love those precise launch times because and here we go. We are getting ready for that ignition. So let's bring it back over to the comnets here, and we'll pick up the final question after the. Yep. So there is a delay to what you are watching because you're watching NASA stream, and NASA stream is delayed on NASA's end. So what you are going to hear...
1 minute now remaining until mesh 2.
So what you are going to hear is you will see about 20 seconds after you hear the call out on the net.
Body rates have nulled out now in preparation for the burn.
Yep. And that's because we're using the NASA feed, and that's how NASA is piping.
Standing by for pre-start shortly. We have fuel pre-start on the RL-10.
And Centaur should be over the
And
Indian
we have
Ocean.
locked pre-start on the RL-10. Now standing by for ignition. We have ignition and full thrust on the RL-10. Chamber pressure looks good.
So again, you just
Body
heard
rate
the
stamping
call
out nicely from startup transients.
Here that the RL-10 has reignited. Everything looks normal. You will see this in about 20 to 30 seconds on your screen because of the delay that on NASA's side, not because of us.
Centaur has gone to closed loop guidance. Body rate response remains nominal, and the Centaur propellant utilization system has gone to closed loop control. System response looks good.
That's all perfectly normal and happening as expected. Centaur is flying per its pre-programmed.
Reaction control system is resuming the loop thermal conditioning firings as expected. Now passing 4 minutes into flight, approximately 6 minutes now remaining in the burn. RL-10 continues to look good. Body rates continue to look good as well. PU system is actively controlling to minimize the mass error.
All nominal, which is good. It's also funny, there was a gigantic crowd of like over 150 people standing with us at the launch, and we are now literally the only two people by the countdown clock and the flagpole are like outside right now at 23:47 local. But all is
passing 45 minutes into flight.
But all is good. All is good with this burn
And
so
we're
far.
approximately 2 minutes into the planned 7-minute burn.
And again, this is the burn to place, to increase the velocity of Centaur and Solar Orbiter to Earth escape velocity, and Centaur is firing its engine and the proper orientation so that that trajectory that it's on when it reaches Earth escape velocity is sending it into the solar system toward Venus.
Body rates continue to look good throughout this burn.
And it will
Chamber pressure on the RL-10 continues to look good.
which is all what we want to hear.
PU system commanding a near nominal MR at this point.
And again, when you hear things like near nominal, don't think that indicates a failure. That's ULA's way of saying everything is going exactly as planned.
Approximately 3.5 minutes now remaining in the burn.
Very good.
RL-10 performance continues to look good.
One of the reasons these burns are so long is also interesting.
And body rates continue to look stable in roll, pitch, and yaw.
Because the RL-10 has a very low thrust
Reaction
but
control
high...
system is continuing its loop conditioning firings as expected.
So a low thrust but a high ISP, if you want to explain to us.
Reaction control system loop temperatures have maintained very close to bottle temps as expected.
Yeah, so Centaur's upper stage engine, the RL-10,
Just under 3 minutes now remaining in the burn.
is very low thrust, but it's very high efficiency. That specific impulse is how we measure rocket engine's efficiency. It's basically how efficiently it can convert the chemical energy of whatever fuel it uses into kinetic energy as in the form of velocity.
And do you know why we measure specific impulse in seconds?
I'd have to go.
Oh, okay. I'm asking because you look at because when you see specific impulse, right, it's always in seconds.
Right. It's kind of an arbitrary. It doesn't mean any unit of time that's any significance. It's just kind of how the math works out. I know that's kind of a cop-out answer, but that's really how. That's really. The
In other words,
explanation
science.
Yeah, science.
Yes. But that high ISP, that high efficiency of the engine is what gives that Centaur that edge over other second stages that are in operation around the world.
Yes. On a related note,
And 2 minutes remaining in the burn.
we've noted earlier that Atlas V is kind of transitioning into using the dual engine Centaur upper stage going forward for almost all of their launches.
The Vulcan.
Well, and Atlas and Vulcan.
Well, Atlas is going to use the dual engine for the Starliner and for Dream Chaser.
Yes.
Yes.
And those missions use that dual engine Centaur because it has more thrust, and that allows them to fly a flatter trajectory, especially for the Starliner missions, which is part of mitigating G-forces should their in-flight abort have to occur. So that's one of those trade-offs where you have low thrust and high efficiency versus a higher thrust but a higher mass for having two engines and thus lower efficiency. So, and that's the kind of parameter that changes mission to mission.
Gotcha. Yes. Very much so. So this burn is continuing. We're waiting for the next round of call-outs, but we
Now
should...
passing 49 minutes into flight. Centaur RL-10 chamber pressure continues to look good. Body rates continue to look nominal throughout this burn. Just under 1 minute now remaining until MECO.
So once this burn is complete, that will be Earth escape velocity. The Centaur and Solar Orbiter will no longer be in orbit of Earth. They will be on a heliocentric, sun-centric orbit, on both of them on their way to Venus.
Yes.
And we'll talk about why the Centaur won't end up doing the same orbits as Solar Orbiter, but
Now 30 seconds remaining until engine cutoff.
but we're going to stop talking so we can hear the call-outs as that engine shuts down.
RL-10 performance continues to look nominal. Body rates look good.
Coming
Standing
up
by
on
for
MECO.
cutoff in approximately 10 seconds. And we have MECO, main engine cutoff.
That's good.
Body rate stamped out nicely from the cutoff transient. Reaction control system is now 100% 4S settling as expected.
So we're standing by for those calls verifying performance. But that...
And Centaur is entering a short coast period prior to spacecraft separation.
So, and what you're seeing there is what you're hearing. You will.
Centaur is now turning to the desired spacecraft separation attitude.
So what you're hearing, you're going to see about 20 to 30 seconds later, because NASA's feed, the feed that NASA pipes out, is
Reaction
about
control system
30
now
seconds
ready.
behind real time. So that's not
As expected.
a delay on our side. That's a delay on NASA's side.
Now passing 51 minutes into flight.
And Centaur is reorienting itself now for spacecraft separation. So that's the next and last major milestone. And then we'll talk about why the Centaur will not do the gravity assist flybys.
Approximately 100 seconds now remaining till spacecraft separation.
Okay, so a minute 40 seconds to spacecraft separation. And again, you're going to hear that call out of spacecraft separation before you see it on your screen, because of the delay that NASA has in their feed that they pipe out to the public. But the Centaur it looks like it did its job. All the callouts were right on the pre-published timeline. So
Centaur
now,
system performance remains nominal throughout this coast period as Centaur is preparing for spacecraft SEP. And a brief review of Centaur performance after the second burn indicates all major orbital elements, apogee, perigee, and inclination, all very close to pre-flight predictions.
that's Iola's way of saying perfect. So perfect performance of the Centaur and all of its burns.
One milestone left.
We should just be a few seconds away. Yeah, one milestone left. A few seconds away from spacecraft separation.
Approximately 30 seconds now remaining until spacecraft separation. Reaction control system continuing the 50% 4S as expected. Body rates have nulled out now in preparation for separation. Same for spacecraft SEP in approximately 7 seconds. And we have good indication of separation of the solar orbiter spacecraft.
That, my friends, is mission success. So expect that tweet from Tori with the number. That is awesome. A successful launch of Atlas V. This was the 82nd launch of the Atlas V. Atlas V is 82 for 82, maintaining its 100% mission success rating from a customer viewpoint. And that's an important caveat because Atlas has suffered a couple of partial failures, one on the Atlas booster, one on the Centaur upper stage. But in both cases was able to recover, and in the Centaur case, get the satellite close enough to its orbit that the satellite was able to compensate for it and the payload customer declared mission success. And in the Atlas booster anomaly issue, the Centaur was able to recover fully and deliver Cygnus into a pinpoint orbit that it was intended to. So technically 2 partial failures, but both customers declared them mission success. So we go with what the customer thinks, and if the customer declares it a success, then it's a success. So 82 for 82 on the Atlas. Solar Orbiter is on its way to Venus. So let's talk about why Centaur won't be doing gravity assists of Venus.
Right, so now that we've had spacecraft separation, we have Solar Orbiter and Centaur both flying freely on roughly the same trajectory. A very slight deviation from the velocity from spacecraft SEP, but everything else, they're both on a track to intercept and fly by Venus. However, in a few minutes, Centaur's upper stage will open all of its propellant valves and the Centaur engine and the tanks to vent any remaining residual propellants and gases within these Centaur tanks, and that will change the velocity of the stage just enough where it will not fly by Venus and not do all of the same maneuvers that Solar Orbiter is now going to do.
Right, it'll still go by Venus,
yes,
but not at that pinpoint trajectory to do the gravity assist.
Yes.
Right. Yeah, so Centaur will be forever in a heliocentric orbit until it hits something or the sun dies. Or technology arrives at a point where we can go get it. But a wonderfully successful mission. We have one more question that comes from Aces Dawn 1. Does Solar Orbiter have any form of thrust for any correction if necessary, or is it entirely gravity assist once separated from Centaur? It does have thrusters, it does have propellant and propulsion on board for course corrections, for orientation, because it has to maintain a pinpoint. That heat shield has to be perfectly aligned with the sun and ever changing as it swings around. So yes, it has propulsion, it can tweak, and in fact it will do some tweaking. That's another reason Centaur will not be doing these gravity assists at Venus and Earth and Venus, is because Solar Orbiter will fire those thrusters to, it is aiming for the head of a pin by Venus to hit just perfectly, so Venus's gravity does just enough to change its orbit and its velocity to swing it closer to the sun. So that's another reason, and it's all thanks to those thrusters and the propellant that is on board Solar Orbiter. And they said a couple of days ago that they actually packed enough propellant onto it so that they can extend its mission out from 7 years to 10 years if it's still good after the end of that. Oh, and we have an answer. So this is what's great about having people behind the scenes.
Yeah.
We asked about specific impulse.
Yes.
We started talking about specific impulse. Specific impulse is the number of seconds a pound of fuel will last when it's being used to produce 1 pound of thrust. Liquid-fueled rockets generally have ISPs, or specific impulses, in the high 400s, and solid-fueled rockets usually have ISPs in the high 200s.
Yes.
So there you have it. It's the number of seconds a pound of fuel will last when that pound of fuel is used to produce a pound of thrust.
So there's your
So why it's in
in-depth physics
so there we
answer
go, and
to
that's why it's in
specific impulse in seconds.
And that's why it's in seconds. So anyway, I don't know about you, Thomas. It's midnight. It is now February 10th, which means we have been up for 18 hours at this point. You may be a little longer because you had a bit of a drive. I want to specifically really thank Michael Baylor, who was our director for all of our live streams over the last few days. The mega one on Saturday, the ones this morning at the pad, the one at Wallops, the one here. Huge thank you and shout out to Michael Baylor for doing this and for being our man behind the scenes, without whom this would not have happened. Huge thanks to Das, too, who is in here and who is at Wallops. He was the one bringing you the live views of Antares on the launch pad. There, Danny, too, for throwing up some questions that were given to us in chat, and Jared as well for throwing up the vast majority of them, and to Chris Bergen as well, who helped us out behind the scenes too.
And thank you to everyone who tuned in today, and a special thank you to all those who send in super chats. We greatly appreciate your support. Without you guys, we wouldn't be able to do what we do, sharing our passion for spaceflight with you guys, so we greatly appreciate it.
Very much so. And make sure to head on over to NASASpaceflight.com to look at our launch and mission preview article. It's not just a launch article. It overviews the scientific instruments that are on board Solar Orbiter, what each one of those instruments will be doing and studying, how Solar Orbiter works with NASA's Parker Solar Probe, and what it helps us understand about the sun so that we can predict when coronal mass ejections, which are these huge energetic bursts of radiation and energetic particles that, if they're thrown at Earth, which happened in 1859, it's known as the Carrington event, which could destroy a lot of our technology. It could take down our power grids. These, Earth and our power grids, we think we're very safe, and that and that our power systems and our communication systems are very reliable. One massive coronal mass ejection at the right moment in time could wipe them out. And this is what Solar Orbiter and Parker Solar Probe are in part trying to answer for us, so that just like we can predict when a hurricane's going to form, just like we can predict when there's a threat of really bad tornadoes, right, or really severe weather, this is what they're trying to answer for space weather that can affect our life here on Earth, our astronauts on the International Space Station, and our proposed colonies on the Moon and on Mars. These are incredibly important missions. They're not just taking cool photos. So go on over to NASA Spaceflight, look at that article, share that article with everyone, let them know what this mission is actually doing and how it will better life on Earth, because it's really hard sometimes when you say a probe is studying the sun And people will go, well, why did we spend money on that? Right? Well, we spend money on it to help safeguard our lives in this regard, and in this particular case. So it is a fascinating mission that is on its way. It's safely in space. Now what we're going to be waiting for are tweets from the European Space Agency on @ESA Solar Orbiter, @ESA Solar Orbiter, all one word, that will confirm the deployment of the solar arrays and confirm that Solar Orbiter is talking to its communications center in Germany.
And yeah, United Launch Alliance has kicked off their launch campaign of 2020 with a successful Atlas V launch. And so far, so good for the ESA Solar Orbiter mission.
And what you are looking at is the streak shot that NASA spaceflight photographer Brady Keniston caught of tonight's launch. Make sure you follow Brady and Nathan and Mike and Thomas. We will go ahead and throw their handles up there. I don't know their handles off the top of my head, but we will throw their handles into the message section of this live stream if you or Michael could take care of that, because please follow them, and Mike Deep as well. Mike was on top of the vehicle assembly building. I haven't had a chance to see what he got yet, but not only will we have the photos that we got here from the press site, in about an hour we're going to be going to the launch pad to retrieve all of our remote cameras, so we'll have a whole host of video and everything but please give them a follow, please give them your support as well as us. But that is going to do it for us here. Thomas, thank you so much.
Thank you, Chris. Always a pleasure.
Yes, indeed. A fantastic launch on time. Wish it could have been a double header with Northrop Grumman, but you as Das said earlier, you'd much rather be on the ground wishing you were flying than be flying and wishing you were on the ground. And Northrop Grumman erred on the side of caution today in scrubbing that launch 3 minutes before it was scheduled to lift off. But we will try again on Thursday for Northrop Grumman. The next launch out of the Cape, which I know is going to be the question, right now is February 15th, this coming Saturday, the 5th flight of Starlink satellites on a SpaceX Falcon 9 from Slick 40 is the current next flight out of here. So thank you so much. If you have not yet subscribed to our channel, please do, and make sure you turn on notifications. We promise we do not spam you with anything other than really cool rocket videos that you're going to want to see. But that's going to do it for us here, live from the Kennedy Space Center. I'm Chris Gebhardt with NASA Spaceflight. Thank you so much for tuning in. Thank you to everyone behind the scenes, and here's to a wonderful start of the Solar Orbiter mission.